future planets form in disks of gas and dust orbiting young stars. To study these disks, a team led by Thomas Henning at the Max Planck Institute for Astronomy, MPIA, in Heidelberg, Germany, launched the MIRI Mid-Infrared Disk Survey, MINDS. Using the mid-infrared instrument, MIRI, aboard the James Webb Space Telescope, JWST, they explore the chemistry and physical properties of these disks, linking them to the characteristics of potentially forming planets. So, what has JWST revealed? Thanks to its high sensitivity and spectral resolution, JWST has detected weak gas emissions that were previously impossible to observe from Earth. Aditya Arabhavi from the University of Groningen explains, "These observations are not possible from Earth because the relevant gas emissions are absorbed by our atmosphere. JWST has identified gas clouds around a very low-mass star named ISO Chi 147, which are rich in carbon-bearing molecules and have a temperature of around 30 degrees Celsius. However, these clouds lack oxygen-rich molecules." Inga Kamp from the University of Groningen adds, "This is profoundly different from what we see in disks around solar-type stars, where oxygen-bearing molecules like water and carbon dioxide dominate. The MINDS program recently found large amounts of water vapor in an oxygen-rich disk around PDS 70. These findings suggest that disks around very low-mass stars evolve differently from those around more massive stars like our Sun, which could impact the potential for finding Earth-like rocky planets in these systems." What does this mean for rocky planets? Orbiting very low-mass stars? The amount and distribution of material in these disks limit the number and sizes of planets they can form. Research indicates that rocky planets similar in size to Earth form more efficiently than Jupiter-like gas giants in the disks around very low-mass stars, which are the most common stars in the universe. This means very low-mass stars host the majority of terrestrial planets. Thomas Henning points out, "Many primary atmospheres of these planets will probably be dominated by hydrocarbon compounds rather than oxygen-rich gases like water and carbon dioxide." JWST unveils a wealth of organic molecules. Using MIRI's spectrograph, the team decomposed the infrared radiation from the disk into signatures of small wavelength ranges, like a rainbow splitting sunlight. They identified a wealth of individual signatures attributed to various molecules. The observed disk has the richest hydrocarbon chemistry seen to date in a protoplanetary disk, containing 13 carbon-bearing molecules up to benzene, C6H6. This includes the first extrasolar detections of ethane, C2H6, ethylene, C2H4, propene, C3H4, and the methyl radical, CH3. However, there was no hint of water or carbon monoxide. Sharpening our view of disks around very low-mass stars next, the science team plans to expand their study to a larger sample of disks around very low-mass stars to better understand how common these exotic, carbon-rich terrestrial planet-forming regions are. Henning explains, "Expanding our study will also allow us to better understand how these molecules form. Several features in the data are still unidentified, requiring additional spectroscopy to fully interpret our observations." For more exciting discoveries in space research, make sure to subscribe to our channel and hit the notification bell. See you in the next video. Until then, take care!